Journey through event-driven systems, we've successfully navigated data consistency and real-time processing. Today, we tackle a challenge that impacts every single byte flowing through our platform: compression. We're diving deep into optimizing StreamSocial's bandwidth, a crucial step for any high-scale application. We'll begin by dissecting the fundamental compression triangle, understanding the inherent trade-offs between speed, compression ratio, and CPU usage. Next, we'll introduce the four core compression algorithms we'll be implementing: gzip, snappy, LZ4, and ZSTD, exploring their unique characteristics. Following that, we'll integrate these strategies into the StreamSocial architecture, examining how compression fits into our data flow pipeline. We'll then explore adaptive compression techniques and glean insights from real-world industry examples like Instagram and Spotify. Finally, I'll guide you through setting up your own compression laboratory to benchmark these algorithms and make informed decisions for StreamSocial. This isn't just theory, it's about making every byte count. At the heart of every compression decision lies the compression triangle. Think of it as a balancing act between three critical factors. First, we have speed. How quickly can we compress and decompress data? For real-time systems like StreamSocial, this is often paramount. Second, the ratio. How much space do we actually save? A higher ratio means less bandwidth and storage, directly impacting costs. And finally, CPU usage. How much processing power does the algorithm consume? Aggressive compression often comes with a higher CPU cost. Understanding this triangle helps us choose the right tool for the job. We'll be focusing on four widely used algorithms: gzip, known for its high compression ratio but slower speed and higher CPU; snappy, which offers a fast speed and medium compression with low CPU; LZ4, the fastest algorithm, ideal for real-time streams, though with a lower ratio; and ZSTD, a modern algorithm offering balanced performance, excellent compression, and tunable CPU usage. Each has its place in a system like StreamSocial. Now let's integrate these concepts into our StreamSocial platform. It's crucial to understand that different data types need tailored compression strategies. A user profile, for instance, has different needs than a real-time timeline update. Our compression pipeline begins with message classification. Here, we analyze the content type and urgency of each message. Is it media metadata, a user post, or a system log? This classification then feeds into compression selection, where we choose the optimal algorithm based on the message's profile and predetermined rules. For example, timeline updates might prioritize LZ4 for speed, while historical analytics might use gzip for maximum stored savings. Throughout this process, performance tracking is vital. We continuously monitor compression ratios, CPU usage, and latency to ensure our strategies are effective and to identify any bottlenecks. This continuous feedback loop allows for dynamic optimization, adjusting settings based on real-time metrics. Intelligent systems don't just pick one compression algorithm and stick with it. They adapt. Our StreamSocial platform will employ an adaptive state machine that adjusts compression based on real-time system load. During a low-load state, we might default to gzip for maximum savings, as the extra CPU is negligible. As load increases to a medium load state, we could switch to snappy for a better balance. During high load, we'd fall back to LZ4 for sheer speed, ensuring user experience isn't impacted even if the compression ratio is slightly lower. In critical scenarios, compression might even be temporarily disabled. Real-world insights reinforce this. Instagram discovered that while gzip compressed profile metadata by 85%, LZ4's 10x speed improvement was crucial during peak hours for user experience. Spotify, dealing with highly repetitive music metadata, found ZSTD with dictionary compression achieved a 92% reduction with 3 times less CPU than gzip. These aren't just technical details, they're millions of dollars in infrastructure savings and a better user experience. Your mission, should you choose to accept it, is to build your own compression laboratory. We'll implement a benchmarking service to rigorously test all 4 algorithms, gzip, Snappy, LZ4, and ZSTD across various data sizes and types. This requires robust data simulation, generating realistic StreamSocial user profiles, posts, and media metadata to truly mimic production workloads. Crucially, you'll integrate monitoring and a dashboard to provide real-time insights into compression ratios, speed, and CPU usage. This will be your window into the performance trade-offs. Finally, you'll design and implement an adaptive system that can dynamically switch compression strategies based on system load, just like the real-world examples we discussed. By the end of this, you'll not only have implemented these algorithms, but truly understand their impact at scale. Tomorrow, we'll take this optimization knowledge into transactional producers, where compression becomes even more critical for maintaining consistency across partitions and ensuring atomic operations. The foundation you build today will directly power those advanced scenarios.